the real OOM, how it behaves, okay, in my Linux here, as well as what is the underlying working of a real OOM when it kickstart, what will happen, okay? Very important stuff. Well, it means that why it's important, because you understand it, then you won't launch it, or you know where to launch it, okay? So this is something that we stopped last time. We talked about the paging system, okay? So paging system is by default is embedded in every CPU since 1990 something, okay? So some of the CPU that you may know about is particularly E and C students, MCU is not having paging. ARM7 don't have any paging. ARM9, some of ARM9 will have paging. So ARM9 can install Linux and run different processes because of paging support. Okay, so remember, paging itself is a very important stuff in order to tell a particular system whether there a process exists, right? If you don't have any paging, then you cannot switch processes very easily, okay? With paging, the ease of switching processes, I mean not ease, but the mechanism start with, you can say for particular process, okay, you have a particular page table which give you a new mapping in order to use the location in your memory, okay? So remember, it is very specific to the CPU itself. When the CPU don't support it, fail, okay? So MCU, ARM7 don't support it, and if you're a CS student, you don't know what I'm talking about, that's okay. I don't ask you in an examination that, oh, what is ARM7 specialties, okay? I don't ask it, okay? So last time we talked about this, the paging support gives you such a fantastic output. Some people already asked me something like, hey, this program give you a surprise that raised by 1 byte, so you give 1 page to me. Now how about I generate another call, still SBR1, which means increase the allocation for 1 more byte. Will I get another page? The result is no. Okay? Because this means that you're rising the level, right? Still remember what's here. The level, water level keep rising. So I'm talking about whether you raise the level up to the multiple of a page. If it's still under the multiple of a page, you still get that page. Okay? And if you raise beyond that multiple of page, let's say from let's say 1 byte, okay, to 4097. So you will get 1 more page because you raise beyond that multiple page boundary. Okay? So this is something that you have to take care of. Not take care of, I mean you understand it. Okay? And then we talk about when I give you a page, basically that page belongs to your process. I cannot share this page to another process because when it grows, okay, you grow your head, let's say like this, okay, we expect that I can occupy the entire page if I am given that page. Okay? So this is something that you have to remember that this is a feature, not bug, okay? Yeah, it's a feature that every CPU implements that way. So we cannot say that, okay, I generate a page that assigned to your process. Can I chop it off in half and give another process? There's no way. Okay? Now, we stop here, right? When we talk about yeah, I know that for different colors here, it means different area of our process. Now we are mapping from our virtual world. Now this is the virtual world in memory space. When your process tries to read out the address, that is in this allocation manner. Okay, the bottom guy is the code. The upper is global, the upper heap, and then the global variables. Now we map it back into our real allocation. You see, I write several blocks here. Okay, so you can assume that every block is a page. Let's say the code is a particularly big code. So you may need 2 pages to host the entire piece of code. Maybe 1 page is for data, that means an initialized global variable, 1 page for BSS, 1 page for the here, 2 pages, and 1 more page for the allocated stack. Now you can see this is no longer continuous because it may end up with an outcome is like this. Okay, something will be put on the RAM. Because this RAM is limited, right? I say that I have a process, I allocate 4 GB. I'm running on a 64-bit CPU, okay? I allocate 4 GB. You also allocate 4 GB, but I am only having 8 physical RAM, okay? 8 GB, sorry. 8 GB physical RAM. So suppose these two guys occupy all the physical RAM. And what are the other pages like the kernel? The kernel also have page. Maybe some others background process you're running browser. They may hide in here, or part of your process allocation hide in here, which is what we call a swap or the virtual memory. Okay? In Windows we call it virtual memory. Okay? Later on I will tell you where to see this. Now this 3 steps together, okay, will give you a picture then from a virtual memory allocation outlook into our real outlook, okay, the real manner of allocation inside the memory. Now, how our process know about whether I have page in the memory or in the hard disk or nowhere? So what is the meaning of nowhere? I give you an address. I shouldn't say this. I am the program, okay? I'm running the process. I suddenly want to get a memory, okay? I give you are the CPU. I give you a virtual page address, okay? Virtual address, and then you try to translate for me, okay? And what I mean is, during the translation, you want to translate the real address. You may find it here, so that means good. It is in the memory, or maybe you fail. What is the meaning of fail? You cannot find it in your, basically you cannot map, okay? You cannot map to a physical RAM. Now we have 2 choices. Either you say bullshits, you give me a bullshit, no meaning address, like 0, okay? You give me null, okay? Then I'm trying to translate the null, of course I cannot find anything, okay? So it will be the case for segmentation faults. Now how about another case is, you give me something, okay, I try to translate it, I fail, but actually it is in the hard disk. But hard disk is very huge, right? Very big, okay? So it's supposed that we don't do the same memory mapping in a page table. We have another way to map hard disk, okay, which is the kernel stuff. Later on I will teach you about this. Okay? So now we take a look at how the page table is organized in order to understand that, hey, where I can find all the pages belongs to me. Okay? So this design of page table. Every books have different versions. Okay? I'm trying to make it more close to the Intel CPU design. Okay? So Intel CPU design is kind of like this, but I removed some of the important stuff. Okay? Important for them. Okay? So what are they? So here is, you can see something like the file system, right? You find the permission, read, write, and then execute, okay? So read, write is easy to understand, right? It means that a particular page, virtual page number, mapped to some, what is the frame number? Frame number is just a name, okay? It means a memory location, okay? Basically, we are talking about making the entire RAM into an array of frames. Each frame is 1 page. That's all. Just names. Okay. You can think of it. Oh, it's a page number. That's okay. Now, I want to map it like this. What is the meaning of this permission? The permission is very interesting. Read, write is easy to understand. You read to the page. You first read from the page, write to the page, and if you have the write, okay, missing, write permission missing, that means that I cannot go to that read-only page and try to write it, and I will get segmentation faults. Okay. And how about execute? Execute is something even more interesting, okay? So I can show you the Google results. So this is Intel CPU execute disable bits. Okay, it is for to minimize the chance of being hacked. Okay, you can not you. Okay, you are not in that level, right? You are still understanding user program. Now this is for the critical end state. Okay, it's for the kernel. The kernel can select a particular frame or particular page, whether it should be able to be executed. Okay, and later on when you go to the security course, you understand why the execution of a piece of memory is so important for hacker to hack things. Okay, so you can keep in your mind that, oh, Intel has such a strange manipulations over a particular frame to control whether it is able to be executed or not. Okay, so you will find null pointer here. Null pointer means that, no, I mean null pointer, it's not a pointer. It means this virtual page number, you know virtual page number means what? Okay, let me go back, virtual page. This guy, okay, virtual page number or virtual page address. Okay, not the full address, but this part. So that means this part, okay, the virtual page number. So why the virtual page number gives you a null? Okay, it may have two possibilities. One possibility is that area is not allocated. That means an unallocated area. So then it will be null. Or it is allocated, but you didn't touch it yet. Okay, so I call malloc, okay, and guarantee that, oh, I get a page. Now, in a real OOM demonstration later, okay, you understand that when I have this allocation, I call malloc. I may have this entry, but the entry say null. Once I try to touch that page, it will be allocated. So this is the magic of something behind the lazy allocation that I talked about last time. Okay, we will connect all the dots and make it into a full picture later. Okay, so now one more bit is called embedded bit, so I have to jump ahead. Okay, so embedded bit means whether that page is in memory or sorry, it's not in memory. Now this is the moment that we know a particular virtual page number when I'm trying to map, I'm the CPU, I'm trying to map whether it is in the hard disk or not, or reverse, in the memory or not. Okay, so this is how we know. So that's why it's very hidden, right? It's really hidden up from the allocation, and the kernel trying to control everything and say that inside the page table you go to the hard disk. Of course, later on I will connect all the stories together and give you a picture that you understand. Okay, so one more is about something here. We have an S bit. Okay, so what is the S bit? S bit is very interesting. It is shareable. Okay, so there is a particular page and it's shared. Now there is a optimization inside every operating system since 1990 something. Okay, why we want to share a page? Let's say you are executing ls, I'm also executing ls. So you load the code, where the code is from a file system, you load it from a memory, put in the memory, and say that this belongs to your code area page, yours. Okay? But now I'm also running ls, okay? While you're running ls, I want to run ls as well. So the kernel already know that this guy already loaded inside the memory. Why not we share it? Since it's read only. Okay? So this is a way to share the memory and I mean, of course it's not anything really important. Okay? So now by looking at this, we already know some of the particular segmentation ports that we've seen before. What are the particular segmentation ports? We try to write a read-only page. Right? This is something that will happen while we started this chapter. I try to write to a string, and that it is not a string, it is a string constant inside code. So you will encounter this, let's say this, okay? You try to write, but the page table, when you try to find me that address, I know that you cannot write. I give a segmentation port from the CPU level. Okay, CPU tell you that no. Okay, I don't know how to map when you try to write. Next is an unallocated frame, like you didn't call malloc, okay, or I should do it in reverse, okay. You call malloc, okay, and then you free the memory. You try to still access it. Sometimes you get segmentation ports because of this. This is unallocated, not being able to map because you return that page to the system already. Okay? So now we cannot see this whole picture connect together. Why? Because we lack an example. Okay? So so there's a short summary over the page. I already talked about it. I want to skip the words. Okay, so now I try to connect all the dots now. Previous demonstration, I later on have two demonstration. One is using a nested function call. Previously we tried to use break or S break. Now one more is using malloc directly. Okay? So this, you already see this, right? And actually when I try to connect this example to the design of the page table, you will find a very little relationship. Why? Because you cannot really see the allocation of the page. What does it mean if you don't really see it? Okay? Because the allocation starts when you call recursion. Okay? You call recursion, then I'm forced to allocate something for you. What is that? It's your local memory, local variable. Okay? Local variable, you have memory. What is that? I make it 512K. So 512K, then approximately how many page? 512K. How many page? Okay. I know you need this. Yeah, 512K. Okay, divide by 4, divide K, okay? So many page, okay? So that means that it's guaranteed that you will have an allocation of new pages. I cannot I cannot continuously use my old page because it's beyond one page size. So I have to allocate more in order that that function is usable. Okay, so I'll roll it. And here is show we have seen this virtual page allocation and real page allocation just change a little bit. Okay, or something like that. Now this is not very clear. Let's make it into a more clear example. This example is much clearer. What is this example? Yes, take a look first. What is the difference between the red area and the blue area? What's the difference? With the green, red. What happened to my eye? Red. With the red area, you will find a virtual page allocation just burst. Okay. What's the burst? That burst is actually telling you one thing in a page table design. Originally, you don't have any virtual page mapped to some memory. So this frame number is now, this permission is now. You should understand that it's not inside the memory. Now, you're trying to expand the consumption. So what is the real consumption there? The consumption is not happen inside the frame, but inside the kernel. The kernel knows you want something. You want something. And this page table, you don't need to change anything. Why? Because there is no real page given. Okay? So what does it mean of no real page given? Let's see it. Okay? So this is only for the top, okay? I missed another terminal. Okay, so let me pull this terminal here. Okay, so let's play with this guy, row here. Sorry, minus what? I can't remember. Yep, minus. Can you see the minus PID? Minus PID, and then this guy. Okay, good. Yeah. I should use Linux, okay? This sucks. Can you see the virtual page allocated something? Yeah, let me go back to Linux. Okay. This is my office Linux. Okay. It won't hurt. Okay. Don't try to be so happy. Yeah, should be right for this example. Nothing will happen. Okay. Let me also SSH there. Go to AWS. Good. Okay. So this is for the top. Sorry, I forgot to launch it. Every time it's like this. Okay, example 1, 2. Okay, so let's grow the hip. This guy. All right. update interval 1 second. Okay, so what this program is doing, let's take a look. First of all, I will print the PID. Okay, and then what's more, I will allocate how many marker, how many mark. It's just 1G of memory. Okay, so take a look here. The virtual allocation is 1G. Okay, if you're not happy enough, I can make it 2G, no problem. Okay, it's just virtual, right? Now you understand that this doesn't hurt me. Okay, yeah, maybe it really changed it. Okay, I love to see big numbers. Okay, wrong here. Okay. Yeah. All right. Did I compile it? Okay. Good. Yeah, some big numbers. Very happy. Okay. So this is the virtual. This is the real. Okay. So that means that the page table don't understand anything. You just tell the kernel that, yeah, I want this bunch of memory. The kernel is just a liar. Okay, really telling lies. Don't tell you whether this is something that should belongs to you or not. Just claim that, yeah, you know, I give it to you already. Okay, you use it. Okay, then something happened with this code. This code now I'm having a pause there because it's waiting for my get char. I have a pause here. Then after the pause, I will do set the memory, really make use of it. And what happens if I really make use of it? You see it? S1, okay. Make it faster. Yeah, 1, 2, 3. Yeah, I can keep on pressing. Okay. So can you see the real consumption get growing? Okay. And what happened behind the screen? Behind the screen is you want to touch that while you're doing MEM set. MEM set you can treat it as a for loop. Okay. Inside a for loop, it set any bytes inside here, inside this PTR1. Okay. It will try to set it one byte by one byte. So that means you're increasing the addresses. Once it's crossed the border of a page, then you will generate some special feature inside the CPU. Okay, so this is the illustration. Okay, so the illustration is I just illustrate what I have done previously. This is a fake diagram, so why it's fake? First of all, you cannot see other processes. My assumption is there is only one process in the system, so that I can easily talk about what happened. The RAM is not that filled. We never have a RAM with only 8-page frame, okay? 8-page frame, how many? Okay, 32K. You never expect there is such a small guys. Now the CPU as an MMU. Okay, so MMU loaded that page table. I just make some random numbers here. I use A, B, C, D, E to represent the page number. Okay, it's not a real number, but just a page number. Then I want to say that this guy I already mapped. So 1, 2, 3, 4. I already mapped 4 guys into the memory. So inside the page table, you will find this. The value is this turn on means it is in the memory, and I get a frame number 0. The BC is also there, and D is this guy, where this is 1, and the frame number is spring. And others I keep now because this is not something that I already allocated really inside the memory, but the kernel know about this. The kernel knows that I already guarantee you 2 gigabyte of RAM. Okay, so let's get started. What happens if I start the memory set loop? Okay, the memory set has for loop. It keeps growing while it's crossed the page border. It will touch this virtual page number E once you cross the border. Okay? Then when you touch it, there is some special phase get generated. Is this the truth or the real self, okay, of segmentation faults? This is the real signal of segmentation faults. There's no segmentation fault signal of CPU. We usually call it page fault. Okay? And segmentation fault is a translation from this page fault by the kernel sent to you. Okay? So this is the layer there. Okay? So this page fault means that something happened inside the page table, and CPU say that actually it's MMU. MMU say that I don't know how to handle. You handle it. Okay? Just like how you work on this assignment. You have two partners. Right? I don't know how to handle. You handle it. Okay? Page fault. And yeah, you do it. Okay? And yeah, you do it. Who is your partner? The OS kernel. The OS kernel know about this. What is this? You cross the page folder inside the kernel. I know that. Yeah, I guarantee that guy. Okay, that process already. How about I tell the CPU to update its page table? Okay, so this is the kernel control to control the page table content. How to control it? There is a handling routine, just like a signal handling routine. Okay, and this signal handling routine is trying to look at its copy of the frames. Okay, inside the kernel you have to do a copy, or you don't know what are being allocated. So you have a copy of the frame inside the kernel. Look into the copy. I know that the number 4 is unallocated, or that guy should be just die. Okay, some performance just die there, so the memory got free, so it's unallocated. Good. I update the page table for you, and tell you that this E now is no longer embedded. I give you the benefit 1. Assign you to the number 4 page. Is that all? No. Okay. I just need something in order to make the program feel better. Is to restart the memory set. Yeah. Very poor, isn't it? You know that you stuck at that line. Okay, I give you a restart. Okay, and that restart of this memory set previously should be segmentation faults. Now it's no. Okay, because the page table is updated, no longer have segmentation fault or page faults. Okay, then the story goes on. Yeah, once you cross the border, handling routine got fixed, and inside the kernel gives you a new page by its control. Now, what happens if I get stuck? What is the problem here? Really get stuck. I get stuck because I run out of memory. Okay? So what's meaning of run out of memory? It means every frames are already occupied. What should I do? Okay? So it depends on whether you have this guy. Depends on whether you have, quit it. Whether you have this guy called a swap, okay? Because my machine has 16G memory, I never need to use the swap, okay? 0. And I can show you this computer. This is the guy, EBC. Okay, let me quit this first. Okay. Double click. Wow, very hot. What? Come on. Okay. So can you see this? I just highlight there. For this computer, I turn off the swap. So you can select whether the machine has a swap or not. Okay? And what is the command? The command is called swap on or swap off. Okay? So if you have been an elite class, you've seen this command. I mean, the first 2 workshop, okay? Swap on, swap off, okay? In order to install the swap inside the system, okay? So the swap means this area is the hard disk, okay? You're welcome to use the SSD as a swap, okay? It's your choice to damage the SSD. Okay? I tell you why it's damaged. Yeah? So now we have to find a victim. So what's the victim? I run off frames, okay? Very natural way is to move one guy, I don't know which, to this swap area so as to make room for the new page allocation. So I need to find a victim. Let's choose the smallest guy, 0, okay? So this guy, you go to the swap. But the swap is not only for your process. Maybe we have many processes already drop their memory in the swap area. So every page that got copied, the swap has a PID. Okay, know that this belongs to the virtual page A. Okay, of this 1, 2, 3, 4 PID. You go there. Okay, and eventually when you want to put this back, okay, we can use these two information to put this back and put it back to the memory. So that's why we need some accounting information there. And this is the whole page 4K. Come to there in order to make room, and it's all controlled, or they have a plan, okay, inside the kernel, okay. The kernel have a plan to copy everything here. Once it finish, it will update the page table so that the page table now is become embedded, no longer in the memory. And the frame number is doesn't care about it because once it's not in the memory, I don't need to look at the frame number. And the last step is update this I, the latest allocation. The latest allocation will change the page table in order as if you have a find new frame and try to allocate it. Okay? So this is what happened during I run this program if I don't have enough memory. If I have enough memory, the story is simple. The story is just like here. You keep on doing the allocation without touching the swap. Okay? And this is the time that you are running out of memory. Any questions? Any question you want to ask? It's very easy to understand if you forget about this page number space. Okay, you put aside the page table, then you say, run out of space, and then you put it in the swap. Okay. Now, what happens if I did it back? What is it? Did it back means someone touched that virtual page number A. I want to delete it back. Oh, sorry, it's not in the memory again, so we will generate page fault. Okay, because it's not in the memory. Now, the handling routine have accounting information, know that, this page A, I just put it inside the half disk, so better put it back. Okay, maybe I select another victim, I will be this guy, okay, you go away. Okay, you put it back to a virtual page A here, under here, H, and copy the H back, the A back to the H location. Okay, just like a simple swap. Okay, that's why the area is called swap area. All right, so this is the page replacement. Okay, and now it's time for me to show this really important program. Okay, I don't know whether this time this machine will crash or not. The machine crash. So I try to make this entire illustration more close to real scenario. So I draw different colors. It means not different components of process, but different processes. Okay, we have a process green, process blue, process red, so on and so forth. Okay, so every page is allocated with 2 MP slots 7 and 6. Okay, and then I kickstart my OOM version. I shouldn't call it version 3. Okay, I missed the version 3 here. I mean we have 3 versions, right? One is the fourth one. Okay, keep on metal but never set it. Second is I changed the global as well as the stack. Now it is no scat, no global, but I use MEM set, so I call it version 3. So let's do it. What happens next? Let's say this guy is a green guy, the OOM guy. Okay. So when you try to just like crazy get the allocation from the real memory, so I don't care about the page table up there. I believe that it's okay. Now this processes, let's assume that they are not very active. Now this guy tries to get everything, and what next is you will experience a time that, imagine you are using very old computer 10 years ago. Okay? You usually find when you launch a process, the hard disk keeps spinning. Okay, you launch Battlefield. Okay, let's say AOE is too less consumption than Battlefield. Okay, so it is better. Okay, so it's start consuming memory, and it's just keep the hard disk activity very high. Why? Because that guy want more, and because you just allocated, and this other processes are so inactive that why not we put the inactive process in a swap area. So the whole memory belongs to that guy. Not the end, because I have the infinite loop. Yeah, more. So this attack, the swap area keeps spinning like crazy now. Okay, you will find your system very laggy, not responding at all. But you understand that I should not press the reset button because you know that something really happened. Okay, and once I continue with more and more swap space allocation, but swap is a limited space. When I have all the swap allocated, all the physical memory allocated, so you can see my reports in the top. The report here. You can also see that the swap has limited size. It will eventually goes full. Okay. So when it becomes full, no, sorry, this is the end of the story. Someone has to be killed, and the kernel define some rules. It's called OOM killer. You can Google it. It's called OOM killer or OOM score. Okay, to score whether you worth to be killed because of OOM out of memory error. So then I will say you secure and kill the process. And this is not the end of the story. Killing the process is easy. After this is extremely painful. Here, nearly countless number of page faults. Why? Every process got swap back. Let's say you start to move your mouse, okay? You want to open a PDF, you want to go to your browser, then every memory that originally put into the swap comes back. Okay? What is my previous, not previous, 8 or 7 years ago, I tried once in my computer during the lecture demonstration, I was S6, okay? When I come back to my office, during that time it's inactive. When I log in, I take 1 minute, okay, to log in. Okay, the login screen don't come back, okay, because the login screen is supposed to be in here. So bring it back, and I forgot to mention that I have a Windows XP VM running. Okay, and every part of that VM memory is in the swap. So the VM gets so laggy that I understand I should not report it. It takes nearly 1 day to recover to something that I feel comfortable with. Okay? Nearly 1 day. Because which part of the inactive memory is in the swap. Okay? So you have to keep on using the computer, and then if you touch something, oh, it's in the swap, okay, come it back. Okay? Very horrible. Extremely horrible. Okay? So don't play this trick. This trick seems to be no damage at all, right? You cannot see this. I need to reboot your computer. I corrupt your file system. No, but here you can understand that once you launch this, you will have a very laggy computer, and you have a disaster basically. Okay, so lots of page faults. And where is the swap? Okay. So in Windows, I don't have Windows here. Oh, actually I have. Okay. So first of all, this Windows 7 license is good. Okay. It's a department license. Okay. Don't think that I'm using some bad copy here. Yeah, that's the power of SSD. Put up so fast. I can't remember. It should be right click, my computer properties, and then advanced system setting, performance, advanced, virtual memory. Can you see this? Virtual memory. Change. So it's having a system managed size of the swap, okay, in a Windows. You can choose no, okay, and you understand what is the problem if you have no paging support. my problem here. Yeah, sometimes you want to learn something, you run out of the memory, someone got to be killed, okay? Yeah, so you can turn it off. And in Linux, is you can use the df command. Df is not for me. Should I? No, df don't have a output. Mount, grab, swap. No. Then I need to do something dangerous. Yeah, very dangerous. P here. Okay, so I have a swap here. What is the command that I just launched? Okay, ED class know about this. Okay, this is the this format command. Okay, so I can see the format of my system that I actually hiding one swap area. Okay, so let's quit it. All right. So one last topic. Okay, one last topic is very important. Just very coherent course. Okay, we start with fog, and we end with fog. Okay, so this is the last topic. So why is I say this? Why we end with fog? Fog has special features, right? I tell you for more than one time that when you call fog, you create another process and you will duplicate all memory from the original process from another. Okay? So you have 1 GB of memory allocation for the original process, then you will have 2 GB total consumption based on the fog. And what is more important is, usually you are doing something stupid. You duplicate all things and forget all things. Because you call execute. Right? You call execute, then you throw away all your previous allocation. So why bother? Why we create a total copy of it, waste all the memory, and throw it away? Okay? So there's one problem. Second problem is, I don't know whether you think about it or not. Let's say I have a process allocating 1 GB, or maybe 2, okay, maybe 2 GB. Okay? And your system only have 4 GB installed. You call fork. Why fork successfully run? Right? You use up your memory already once you call fork. Okay? Why is support that feature? And how to resolve this? Okay, actually there's one problem with 2 sides. Okay? The problem is why we do it. Or is there any way we can do better than duplicate? Okay? So this is the ending part, so it's maybe a little bit hard to understand. We play some tricks in page table during the time we call fork. Okay? So what's the trick that will be performed in a page table? We call it a cow. Okay? Cow. Copy or write. Okay? This technique is not only happen in memory, but also happen in file system. We have copy and write file system. We have copy and write memory technique. Okay? And this copy and write means I know that I will create a duplication. No problem. Okay? I promise you I do it, but actually I didn't do it. Okay? I promise that I duplicate it, but never duplicate. Once you try to write to the duplicate content, I split 1 into 2. Understand what I mean? I delayed that copy. I delayed it. Okay? And the delay in a high level point of view is back to this figure. This is another line. Okay? Yeah, operating system for line. I cheat you. Okay? I tell you that this duplicate, no duplication. No duplication. And what happened is, once you try to update variable, maybe the first variable you updated is PID equal to fork. Okay? PID equal to fork, the 2 process will give you 2 different PID output, right? And you save on different variables. And this is the moment that you try to write. Once you try to write, let's say your PID equal to fork, the PID is a local variable here, the stack. I start to create another duplicated page of the new stack and give it to your process. And how to work on this special technique based on the page table design, it's not hard. Okay. Now this is the original page table of process A. Let's assume that when I do fork, you will create process B. And what is the update? The update is you don't need to really copy any memory. What is being copied is page table. Okay? Copy the page table. So what is the result? The result is very interesting. Let's forget about the highlight area here first. We do a copy. That means that when I have a page, that page belongs to the local variable. Let's say the local variable is a virtual A, maybe. The local variable is shared. It seems to be shared. Why? The page frame number are the same. That means the array inside the memory, they are of the same slot. Same slot. Okay? So all memory point the same slot, that means that no real allocation of new page happen. And what is the protection here? The protection is a permission change. Why we need a protection there? It means that, let's say these two guys were trying to run together. So if you don't do this protection, you duplicate the permission here, let's say the writable page, they do write to the same memory allocation. There's no way to stop that. We want to stop the write at the same time. So how to stop it? Easy. Just don't let it write. Right? Change all the permission to read only. But it sucks. Why it sucks? That means that you duplicate a process, then you make every page become read only, and you get segmentation force once after fork. Okay? Yeah, that is not the end of the story. Remember, there is a concern. Two processes want to write together. You give a block there. Yeah, don't write. Let me handle it. What does mean? Let me handle it. Okay? You try to write. Go ahead. When you try to write, I will have page fault here, and page fault will not directly convert into segmentation fault. Every time, the kernel needs to understand what is that fault. Hey, tell me. Oh, that fault is by the design of my copy on write technique. By copy on write technique, I know that you just being forked, and some accounting information inside the kernel knows about this. And once I know about this, okay, no problem. These two pages, now you guys share them, no problem. I make it into two different pages. Okay? And fulfill the promise now. I duplicate it. By duplication, I create two different pages, and of course something I didn't write in here, the real page 10, okay, in the memory slot 10, will be copied all data from the slot 1, copy there, so that you will have a new page to write to. Then next, let's say this process B want to write to the B, no problem. You will make it into write because based on the accounting information that my promise is fulfilled. I really could have copied it. So here I can make it W without any changes, further changes. I mean. So this is a copy on write technique. It's also happened in the file system. File system, you want to copy to file. Actually, some file system will just tell you that I copied the file, but actually they are not copied. Once you try to modify the file, I start giving you the reflecting the change by storing those change block. Okay? It's also happened in the Git system. Git system is doing something like this. They do a comparison. What are the changes? I only say the change. Git, you know, Git, GIT. Okay, not GIT. Okay. GIT. It's also doing this copy and write technique. So the copy and write technique is very common in a system side. Something that is hiding from you guys. You never asked to write this program, but you use it every day. Okay? So this is the end. I need to reserve some time to talk about the examination. Okay? What is remaining here is about the replacement algorithm. So if you're interested in reading ahead, you can, that means that the algorithm is very easy to understand. Basically, it's talking about why or how we choose a victim. Okay? And who should be the victim. So this is the remaining part. Any questions on the copy and write? No questions? Yeah, the mechanism is kind of complex, but the idea is very easy, right? We do a duplication, we save the change overlay. Okay?